the probability for finding an electron at the position r at the time t. In the next lecture, we will continue with the discussion of the Schrödinger equation and the interpretation of the individual quantities by talking about operators and their expectation values. Let us talk about operators and their expectation values. So far, our board is quite empty. We only have the Schrödinger equation and the interpretation of the wave function as a probability density. However, we can next introduce operators following the correspondence principle. So if you remember from one of the previous lectures that we have calculated these derivatives of the wave function. So the time derivative and the second derivative with respect to the coordinate x. And in the end, this gave us an energy as a prefactor and some momentum square as a prefactor. So as a consequence of this, we can say that this here, the I h bar and the partial derivative with respect to time can be identified as a so-called energy operator. And the same goes for the momentum. Here we just have to be careful because this is p square, so we have to find an operator that when squared gives us this one here. So we can say the momentum operator is h bar over I times the nabla operator. So what's really important when we talk about operators is that by themselves they don't mean much. They have to act on the wave function. This is, by the way, also true for the nabla operator. The nabla operator just is a vector of partial derivatives, but these derivatives mean nothing. They just have to act onto another function before they can actually be calculated. And the same is true for the energy operator and the momentum operators. They only return numerical values when you let them act on the wave function. And in fact, if we let such an operator act on the wave function, they will return their eigenvalue. So an operator acting on an eigenfunction will give the eigenvalue times this eigenfunction. And now, besides these two operators, we can also define the Hamilton operator, which is the momentum operator squared over 2m plus our potential. And so we can write down the Schrödinger equation in such a way. Now, let us add these important things to our board. So make two more sticky notes. Here we have these two operators, and here we have the Hamilton operator. Now with these operators, we can calculate their expectation values, because as we have learned previously, an electron may be measured near its nucleus, but when you measure it many times, it will really be measured in a whole cloud, a whole distribution of the probability density. And the same also holds for other operators. For example, we can calculate the expectation value of the momentum operator by this expression here. And in general, we have to integrate over the wave function operator and the wave function. And then we have to integrate over r, also here. Now, this is also something very important, so we will add this to our board. And for the position vector, we can do the same thing, but here it's kind of trivial because the position vector is basically just the position vector. And therefore we can write position vector times absolute square. And this is much more easily to be calculated compared to the momentum operator. So now let's do this for our previous example where we had this Gaussian function. So for the position operator, we integrate over r times this Gaussian function, and since the Gaussian function is centered around 0, it will give 0. So on average, we expect the electron to be inside of the nucleus. And a similar thing will happen later in one of the examples that we will calculate, where we have such a box with a potential that looks like this, and we will see that the wave function looks like such a sine function here. So when we calculate the corresponding probability density, this will have two areas, one on the left, one on the right, where the electron can be, and it can never be here exactly in the middle, where the wave function is 0. However, when we calculate the expectation value, we expect the electron to be here, on average. However, the electron can never be there. So if we measure many times, we will never find an electron here, but on average, this will be the result we will get. So this will be the expectation value. So these are two, let's say, counterintuitive examples that show you that the quantum world is a bit crazy. So here we expect to find our electron inside of the nucleus, which is of course not really possible. And here we expect to find the electrons at A/2, even though the probability density is 0 here, and we can never actually find it there. But please remember, these expectation values can be understood as averages over many measurements, and then it can make sense. Okay, and this could also be a bit of reminiscence of Schrödinger's cat, because it is like the superposition of these two states, and overall it's then just the combination of these two states, even though this sometimes doesn't make so much sense from a classical point of view. Great, now we have finished our discussion and interpretation sections, and we will conclude this whole section with an intermediate summary.